the equilibrium constant lab. So I'm gonna like grab my cam here. All right, so this is the one that, of course, to me it looks backward. All right. Okay, so experiment 34, this is the one that everybody did over the past 2 weeks. Okay, and then we've got information up here at the top that says molar concentration of your iron and molar concentration of your NaSCN. Okay, both of those things should have information that is over here at the top of table 34.1. And I'm all, to me, it looks all fuzzy here. But anyway, that was where part A's information came from. And so then if I swivel around here and we look at the things that are down the side, and I'm going to pop open a document and kind of show you what they're looking for here. Okay, so I created a Word document. All right, so the first one asks you what the volume is. So when you are looking at the table 34.1, okay, there are a list of how many milliliters that you'd be using. So let me pick on one here. Let's pick on the second one, and we'll say that 2 milliliters would be the volume that was used in solution 2. All right, to do your moles, okay, one of the things you're going to have to do here is convert your volume from milliliters over to liters, because otherwise your volume is going to end up with like the wrong unit set. And we're going to multiply this by 0.001 moles per liter. And this is of your NaSCN. Okay, so think about what that does for you. It's like you do liters, and let me put a little multiply sign here, okay, times molarity. That way my liters will cancel out, and I will end up with a number of moles. All right, to get the next line here, note it has square brackets on it. Square brackets means you are in molarity again. So you're backtracking your way through this. Open up my other binder here so I can look at my version of the sheet. All right, so then it says, molarity of SCN, okay, and you're going to have moles of your SCN, and this is from the line above, okay, this is from A2. But when I created them, since I did this in the lab before you guys got there, and you just took your samples and put them in the cuvettes, I did them in 25 milliliter flasks per the instructions from the lab book. So when you have that, that's going to give you molarity. So 2 milliliters. And then if I multiply those two things together, that's going to give me 2 times 10 to the negative 6th. If I then, in the next line, divide by 0.025, then we get a little bit different value out of this. I'm going to get 4 times 10 to the negative 5th. So we actually have a slightly bigger exponent because this one here, okay, that one's only moles. No liters involved, liters canceled out. the line below, since you are dividing by less than 1 liter, you get a larger exponent. And then A4 means that you are supposed to make an assumption, okay? They give you FeSCN plus 2 in little, oops, it's supposed to be plus 2. And this is all in square brackets. And so we're assuming that it will be the same as A3. So I'm going to have the exact same number that I had above. And we talked about this a little bit in lab, in that the reason you are allowed to do this, my exponent did something flaky there. The reason that you are allowed to do this is your thiocyanate is your limiting reactant. You have way, way, way more iron than you actually need, but it is the thiocyanate that controls how much product you can make. So we make this assumption that if everything went according to plan, you would use up all of the FeSCN to do this, and that would give you an equivalent amount of product. A5 on your lab sheet there, you can leave blank. If you recorded them, that's fine, but we don't really need them. It says you're supposed to record %T there, but we know from one of the previous labs that we did that %T doesn't give you a linear graph. %T actually gives you a curved graph, which is not great for predictability. So we're just going to ignore that. If you did go ahead and read the %Ts while you were in lab, just leave them there. We're just not going to use them as part of the calculations. And then the A6, this is your absorbance values, okay? They should be somewhere between 0.001 and 2. Well, actually, technically 1.999. Okay. Remember that they should have been increasing as you went across. Okay. That way, it will give you a nice, relatively linear graph by the time you actually create your graph. All right, so your graph should look, obviously on Excel, okay, something like this, okay, and we're going to have absorbance as your y-axis. You're going to have your FeSCN concentration as your bottom, and then you're probably going to have, let me create some points here. All right, and then obviously your trend line. Oops, undo. That was really awful. Probably something like this. Not all of your dots are obviously going to be right on the line because there's always some variability. But once you do the trend line, you should get pretty good correlation. Usually people get about 0.96 or 0.97 as their R value at least. You might end up doing better than that, depending. If it's under 0.9, double check your math. I tried to make sure I looked at everybody's data before they left for the night on the nights that we did this. I don't remember seeing anybody that had data that looked super glitchy. So you should be able to create your graph and get a pretty decent linear graph out of it. All right. Let me see if I can get my Excel spreadsheet to pop open. All right. When you're doing your Excel, so I'm going to have relatively small values for my concentrations. I'm actually just going to go ahead and do them in decimals as opposed to doing the times 10 to the negative, because sometimes Excel can be fussy. Did I put enough zeros in there? Nope, I did not put enough zeros in. Because those are supposed to be times 10 to the negative fifth. Yeah, this one needs another 0 in here. Because that way it'll do that one and then 4 zeros. So yeah, that should be 10 to the negative fifth. All right, so this one does not have as many zeros. All right, so those are, I just invented some numbers to show you kind of how this looks. So 0.232. If your numbers are a little lower or a little higher, that's fine. Because everybody's machine is a little bit different. So choose your scatter graph. We want one with a line on it. And boing, I have a graph. Okay. And I want to right click on one of my dots. I am going to add trend line. And I want an equation and an R value so I can tell how decent my data is. And yeah, so I got a Y value of, or Y equals 10,629 plus 0.0092. So yeah, I've got pretty decent data. I can also look at my R value there. I'm really close to 1.9996. And so if I wanted to go back and show you how I'm labeling this. All right, so we're going to do FESCN versus absorbance. And then click on this, and this is my absorbance part. So yes, and this is my CN and in molarity. All right, so, oh, and it's being fussy. It deleted my trend line. That is one weird goof about some. I have a slightly older version of Excel. I don't know if the latest version actually will accidentally sort of delete your equation if you label it, or if you do the trend line and then you label it. Mine does that. It somehow decides that you hadn't chosen to do the trend line yet. So usually I have to go back and reinvoke it. But okay, this simulates your part A data. All right. Now back to my Word document. All right, once you're all the way done with part A, all right, and the next thing you have are the part B bits. So by the time you've crunched all through the data for that, and you get your down to B6, so you get, for instance, if your B6 absorbance was 0.252, okay. Calculations are all part C. You need to put this value, 0.252, in as your Y into your equation from your trend line and solve for X. And I end up with 4.57 times 10 to the negative fifth, because all of my concentrations when I did the graph were all 10 to the negative fifths. Okay, as you crunch your way through this, the next thing it's going to ask you for is moles. Okay, moles of FeSCN. So you have a concentration now, but this was done in that little flask, the little shrimpy flasks that we were using, and we had a total volume of 10 mils. And so your C1 value, in this case, it was the 4.57 times 10 to the negative fifth. And then I'm going to multiply that times my 10 milliliters, but make sure you are doing it in liters. If you try to just simply multiply by 10, leaving it in milliliters, your decimal is going to end up in the wrong place. So this would give me something like, okay, the front end doesn't change, it's still 4.57, but my exponent changes and it becomes 4.57 times 10 to the negative seventh. Okay. And each of the lines in the Canvas instructions tells you how to progress from each step to the next step. It goes, okay, when you get to the next line, do this. When you get to the next line, do this. So you should be able to crunch your data and get all the way down through C9. C9 being the one where it actually asks you to calculate your equilibrium constant. It should be in the hundreds. I will tip you off that much. Definitely not less than 1. Okay, definitely shouldn't be bigger than 1,000. Okay, hundreds is what we're hoping for based upon your data. So this gives you at least a little bit of extra information on how to do some of the number crunching involved for that lab, because it's a relatively complicated lab. We don't have that many labs left. One of the things that I was actually looking at prior to turning on my Zoom is the fact that, so last week and this week were equilibrium constant and Le Chatelier's, which is watch the video and answer the questions. Next week, we are doing, it's called the potentiometric analysis, which actually is, okay, there's 2 parts. One, this is the only lab that we do this semester where the pre-lab and the lab report are actually sort of technically designated as 2 separate weeks. My A group people will be actually doing the titration on the 31st, so 1 week from yesterday. And then going back and doing your handout, which is the pre-lab part, the following week. And then my B group people will end up doing the handout first and then doing the titration. We are doing this for a diprotic acid. And then after that, there are only 2 more labs, one of which, of course, is real. And the other one is simulation data. So we have molar solubility, which is a titration lab of a different kind. A group is doing that on the 14th, and B group is doing it on the 21st. So we are nearing the end. So keep an eye on the end date for this. We have May 3rd as the day you have to get all your lab stuff to me because I need 48 hours and it takes forever to grade stuff on Canvas. Okay, so kind of keep that in mind in terms of lab stuff. All right, let me flip-flop around here for a moment and find my KSPs and buffer notes. I want to go through at least a little bit of that tonight. All right, so KSPs and buffers. We did down to Henderson-Hasselbalch on Tuesday. And the first one we were looking there in terms of the Henderson-Hasselbalch really focused on a buffer that had an acid plus a salt. So acetic acid plus sodium acetate were the two components of your buffer. You can actually use the same equation with a little tweaking in order to be able to do it for a weak base and a buffer. And that's what the next example is about. We have some ammonia that is 0.35 molar. So that's your weak base. Your NH4Cl, of which we don't care about the Cl part, is your salt. So think about this in terms of, okay, what am I using in terms of pieces to set this up? Your equilibrium equation looks like the NH3 plus water, because these are all done in aqueous solution, gives you NH4 and OH. But remember, we have all these things together in the same beaker. And weirdly, I'm not really sure why, but 1.8 times 10 to the negative fifth is the KB for ammonia. It also is the Ka for acetic acid. I'm not really sure why they're identical, but most textbooks cite them as identical. However, my equation doesn't allow me to use a KB. Okay, so scroll back up here a little bit. Look at your equation here. Okay, the equation that I'm using, pH equals pKa plus log of conjugate base over acid. It has to be in that format. So in order to make that work, I'm going to use my variation on a theme. Okay, since here's my KB, the 1 times 10 to the negative, 1.8 times 10 to the negative fifth. We know what KW is. We know what KB is. Do your division. And my Ka ends up being 5.6 times 10 to the negative 10th. It is a very low Ka. But then I can actually go back and put this into my equation, because here's pH, so P negative log of my Ka that I just calculated, and look at my values here inside my second set of parentheses. Remember that it has to be base over acid. Put your ammonia on the top because it is the one that is actually the base. Put your NH4 concentration on the bottom. It is your, it's a conjugate acid, but it's still an acid. So B on the top, A on the bottom, and it has to fit that format. If we look at the math for this, taking the negative log of, actually, let me go back and fix this so that it's more obvious. So negative log of 5.6 times 10 to the negative 10th. And then log of my value there in the parentheses will give me negative 0.196 This is a base and salt buffer. It has to be above 10. Actually, not 10, has to be above 7. Because 7 is neutral. So if I have a base and a salt, that's going to give me a much higher pH than my acid and salt combination. Think about this in terms of kind of big picture ideas of what am I starting with? If I'm starting with something that's a base, got to be above 7. If I'm starting with something that's an acid, it's somewhere below 7. So kind of think in terms of how these parts fit together. And then I wanted to introduce a little bit of reality in some ways. If you ever do lab work in a medical lab or a lab that uses proteins, they usually use the phosphate buffer system. And so the way that this works is usually you make up a recipe, some 0.2 molar of the sodium phosphate that has 1 sodium and 2 hydrogens. And you make up a liter of the other stuff, which has 2 sodiums and 1 hydrogen. And then you use a ratio. So for instance, if I knew that I was shooting for a pH of 5.7, once I've got my recipe, I can use X milliliters of A and Y milliliters of B, put it in a volumetric flask and fill it up with water up to the 200 mil mark. And I automatically know, give or take a little tiny smidge, I already know what my pH is going to be, okay? Because the ratio of those 2 substances is actually what determines your pH. And it really does all swing back around to the Henderson-Hasselbalch idea. A couple more buzzwords here. Buffering capacity. So buffers are not unlimited, okay? If you dump enough H plus or enough OH minus, you can overwhelm them, okay? Basically, it kind of overflows, chemically speaking. The buffering capacity is how much you can put in without much change. So like back earlier on Tuesday, we were looking at adding 2 mils of a relatively concentrated acid to some of our buffer solutions. You could probably add probably 15 or 20 mils, likely, before you start running out of the ability to buffer against the pH change. And it really depends upon your magnitude, basically how concentrated is your acid and how concentrated is your conjugate base. So up here, my recipe, okay, look at my values. I've got 0.2 molar. In the world of buffers, compared to some of the other things like these, we've got 0.2 and 0.4. For the base one, we had 0.3 and 0.5. Okay, those are all fairly typical, okay? You might be able to construct a stable buffer from like 0.5 molar, which would give you more buffering capacity, causes other solubility issues to some degree. But it really does depend upon how much of your substances are present. And if you want to pick a buffer to match a pH, okay, we saw that looking here at my combo of phosphates, probably, okay, this one had a really small amount of Y in it. I probably can't get a pH much lower than about 5.5. And since I'm shooting for having a 200 milliliter volume of this, I probably can't get a pH probably much above 9 for that. So it's kind of somewhere in the middle. Most of the acetic acid buffers are in the 5 to 6 range. Most of the ammonia-based buffers are up in the 9 range. There are ways to tinker with it to make it a little bit lower or a little bit higher, but they're less common. But you can match things. Remember, P is a function. P means negative log of. So whatever pH you want, if you choose a scenario that has a pKa similar to your pH, then whatever changes you make to the concentrations are going to be kind of in the same relative pH area that you are shooting for. All right, so that is the end of the buffer portion. I want to do a little bit of solubility. So solubility in first semester, we tended to present to you as, yes, it's soluble, no, it's not soluble, okay? And there were 6 rules. Things like most nitrates are soluble and most chlorides are soluble except silver, lead, mercury. Most things with sodium, ammonium, or potassium are soluble. We just kind of presented them as rules. That's not entirely true. This is sort of the way chemistry is generally taught of. We teach you some broad stroke ideas to start with, and then the further you get into it, we kind of backpedal and go, no, it's actually a little more complicated than that in reality. So that's kind of what we're doing here. So back to that chloride rule. One of the chloride rules that we dealt with in first semester said most chlorides are soluble except silver, lead, and mercury. Well, that's, again, not exactly true. It's not like we're going to totally reverse the situation and say, oh no, silver's soluble. We are going to reverse that idea just a little bit and say it's slightly soluble. Okay. This is more variations on equilibrium. So look at my silver chloride thing here. So silver chloride is composed of 2 ions, the silver ion, which is the metal part, and the chloride ion, your non-metal part. It has a very small solubility. Think of it kind of, remember the giant flask we had sitting on the cart in lab over the past couple of weeks for collecting all of our waste of our iron thiocyanate. It's a 2-liter flask, okay? If I had some powdered silver chloride, I could probably get a 0.5 gram or so of that to dissolve in a full 2 liters of water, maybe even a little bit less. So it does dissolve just a little bit, but not very much. When you reach that point where you can't get anything more to dissolve, okay, back to sweet tea, which I think is nasty crap, is to be truly Southern, it's like take the warm, we talked about this a little bit when we were talking about solubility as a general idea. you take the warm tea and you stir the couple cups of sugar into it, and you keep on stirring until it's kind of weirdly crunchy in the bottom, which means there's not going to actually get any more sugar to really dissolve. Well, that's a saturated solution. Unless you change the temperature, you're not going to get any more of your substance, in that case, the sugar, to dissolve. More fun new letters of the alphabet to use as subscripts underneath our capital letter Ks. We had KCs and KPs, then KW and KA and KB. Now we've got KSP. And the SP stands for solubility product. All right, so let's look at the description. However, the description is a little bit of a brain twist because of the way they state it. They tell you that it's a product of the molar concentration of the ions raised to the power of the stoichiometric coefficient. Okay, which is true. Okay, everything stated there in that definition is actually true, but the way it's stated tends most people to kind of scratch their head a little bit and go, what did that actually mean? So let's pick some more on my silver chloride. I'm gonna write this kind of like when I did my pHs, in that there is no bottom to my equilibrium expression that has a K in it. When we did KW, we said it was H plus in square brackets times OH minus in square brackets. And we didn't write the water molecules on the bottom. The same idea kind of happens here. I'm going to hop back over to my whiteboard for a minute. All right, so here's my silver. And then I have my chloride. But what we're actually running into here is heterogeneous equilibrium. Okay, because my silver chloride is a solid. Okay, because if I write this, okay, I would have AgCl solid. Okay, and then I'm have my little double-headed arrow here. And then my Ag plus and my Cl minus. Okay, now both of these, this bit here and this bit here, are aqueous. That one's a solid. So back at the beginning of the equilibrium chapter, one of the things we said that we could do with this is call this K prime, meaning I'm in the process of working it out, but it probably has some things in it that I won't actually see once I get to the end. And that's kind of what's going on here. So flipping back over to my file here. I have Ag and Cl, there's no bottom to it. Okay, like I said, it looks an awful lot like when we're writing out the expressions for KWs. They also all are really small. Now, unlike KW, which had a limit, once you got down to 1 times 10 to the negative 14th, that was kind of the bottom basement. That was as far down as you could possibly go. Now, the number that I looked up for my silver chloride, this one's slightly larger than that. okay, 1.6 times 10 to the negative 10th, but they can go a lot lower, okay? And I gave you here the general statement of the smaller the KSP, the less soluble. So let's pick on lead sulfide, okay? Another little 2-component molecule here. We've got lead, the +2 version, and sulfide. If you look up the KSPs, and there is a table, again, I think there's one both in your chapter and in the back of the book. You'll see here, this is a lot smaller. 3.4 times 10 to the negative 28th. Now, and I will kind of circle back to this again next week, is I will say that anything that claims to have a KSP value with a negative 50 exponent or smaller, like negative 60 or negative 70, is pushing the limits of reality, okay, in terms of actually being able to calculate KSPs. So if you're doing problems, if you're looking at examples, either in your textbook, on the web, whatever, and you see things that imply your KSPs are way, way, way down there, like I said, negative 50s, negative 60s, negative 70s, either assume that they are doing that kind of a calculation to make a point, or assume that it's not realistic. Okay, mathematically maybe calculatable, but possibly not realistic. Okay, we also see no units again. None of the capital K values that are used over the past few chapters have unit values to them. Unlike the lowercase k's from kinetics, they had units, things like per second or molarity per second, or flip-flop and do seconds over molarity. All of these K values actually have no units. So keep that in mind in terms of things should cancel out. All right, that gets us all the way through about 60% or so of this chapter. I'm trying to give you guys also a little bit of time to help catch up on some of your lab stuff, because most people owe me stuff. So keep that in mind and crunch away at your lab stuff over the next few days. If you have not turned in your acid-base equilibrium yet, I know a couple people turned it in and some people haven't. Make sure that you get it turned in tonight before the midnight due time. And then I will end up going through the answer key to that next week. I want to get through another big chunk in this latter half of the chapter also on Tuesday. So kind of begin to think about the fact we have 2 more chapters that are soon going to be finished. The acid-base one combined with the buffer KSP one, that's another pair that will become the following test. So the next test will probably be, let's see, this is the 25th of March. Maybe, I actually need to pop open my calendar here so I can see what I'm looking at. Probably the weekend of the 9th and 10th is my best guess for when the next test will occur. And that will be test 3. And then there's one more test after that, that is thermo, the second half, we're going to do kind of selected parts of electrochem and some selected parts of nuclear. And those are all on the 4th test, with the final exam being, I believe it's the 5th of May. Let me scroll down here on my, actually, you're probably going to have a 2-day window for the final exam. It's probably going to go live at midnight on Tuesday the 4th and probably be due by midnight on the 6th. So kind of pencil that in too as when the bitter end occurs. Questions? I am missing at least 2 people, I think 3 people, and maybe a couple more. So I guess everybody kind of, I don't know, was elsewhere tonight. Questions about homework?
No question, but I'm using my daughter's computer, so it's not Jordan, it's Venetia, it's V.
Oh, okay. But yeah, I still have several other people who I don't see any kind of a login for. So anyway, hopefully they will read notes, and I will eventually get around to posting this since I did hit record. But work on labs. Okay, everybody's behind. Which I know it really sucks. The not being able to like ask questions every week is just really hard. But I'm trying to give you as much information on video as I can. Otherwise, I will see you on Tuesday.
Thank you.
Bye-bye.